Welcome to this deep dive. Before we start, I want you to just look around the room you're sitting in right now.
Yeah, to your eyes, it probably looks pretty empty.
Right. Just the air between you and the walls.
Nothing to see.
But if you could suddenly perceive the electromagnetic spectrum, you would be absolutely blinded.
Oh, completely blinded.
Because we are constantly swimming in this ocean of radio waves.
Constantly.
They're propagating through the physical space right around you, carrying, everything from your text messages to complex Wi-Fi data packets,
Cellular infrastructure traffic.
emergency broadcasts, top secret communications.
All of it. It's an incredibly dense, invisible highway.
And it is operating at absolute maximum capacity.
It is. It's a vast, unseen ecosystem. And because our entire modern infrastructure relies on that ecosystem functioning flawlessly, we can't just let it operate unmonitored.
Right, which brings us to the mission of today's deep dive.
Exactly. We require sophisticated methodologies to map it out.
To analyze it.
And to effectively police it, so all those competing signals don't just collapse into a wall of static.
So today, we are exploring the mechanics and the real-world applications of radio frequency sweeps.
Or RF sweeps, as they're commonly known.
RF sweeps. And our goal here is to really understand how engineers detect, monitor, and police this invisible landscape.
It's a massive topic.
It is. And to do this, we're drawing from a foundational Wikipedia overview to get our bearings, but we're also pulling from some heavy-hitting sources.
The real industry Bibles.
Yes, the National Association of Broadcasters Engineering Handbook.
The classic.
And the Electronic Engineers Handbook.
And those handbooks are crucial because they provide the pragmatic, boots-on-the-ground reality of RF engineering.
They move us past the theory.
Right, past the theoretical physics of a radio wave and into how we actually measure and manage the spectrum in real time.
So let's lay the groundwork. How do we define an RF sweep based on these sources?
Well, fundamentally, an RF sweep is the process of scanning a specific radio frequency band with an adjustable receiver.
To detect what signals are currently transmitting.
Exactly. You're sweeping a receiver across a target band, and you're looking at the amplitude.
The strength of the signals.
Right. The strength of the signals across different frequencies along the way.
Okay, let's unpack this. Because visualizing the invisible requires some very specific tools of the trade.
It does. And the primary standard instrument for this process is the spectrum analyzer.
The spectrum analyzer?
Yeah, it essentially acts as a highly sensitive, tunable window into the RF domain.
So you have the tunable receiver architecture doing the sweeping.
And that's connected to a display that graphs the waves. It plots the measured two-dimensional power spectrum.
Let's talk about that graph.
Yeah.
Because anyone who works with these instruments knows that display is everything.
It's the primary interface.
Right. So you have two axes.
Yeah.
The measured power is on the y-axis.
Going up and down.
And the frequency is on the x-axis, left to right.
Exactly.
Yeah.
But the real challenge here, the thing engineers have to wrestle with, isn't just scanning. It's the sheer dynamic range.
How you scale that power measurement on the y-axis.
Yes. And you have a choice between linear units and logarithmic units.
And linear is pretty much a non-starter, right?
Oh, a linear scale is completely impractical. The handbooks are very clear about this. I mean, the power disparity between a massive, intentional broadcast signal and a tiny, unintentional, faint signal can be staggering.
Like millions of times different.
Millions, sometimes billions of times in raw wattage.
Wow.
So if you plot that on a linear scale, your big dominant signal will just shoot right off the top of the display.
And the smaller signal.
They get completely compressed into the zero line at the bottom. They become totally invisible.
It's like trying to hear someone whisper.
While standing next to a jet engine.
Exactly. A relatable real-world analogy. The jet engine completely masks the whisper if you're measuring linearly.
Which is why spectrum analyzers default to logarithmic units.
Usually measured in dB, right?
Yes. Decibels relative to a milliwatt. A logarithmic scale mathematically compresses that vast power difference. It provides a much larger dynamic range.
So you can see both the jet engine and the whisper on the exact same screen.
Precisely. You can see massive signals and tiny, faint signals side by side with incredible detail. It's such a vital feature.
Okay, so we have the graph, we have the log scale. What about the pace of the sweep? It doesn't just happen instantly.
No, it takes time. Sweeps move continuously from a minimum frequency to a maximum frequency, or vice versa.
And they do this at a fixed controllable rate.
Right. The sources give a specific example of sweeping at a rate of 5 megahertz per second.
Which sounds fast, But across a huge band, it takes a moment.
It does. And you have to control that pace to get an accurate reading.
Okay, so we're sweeping across the band, measuring power on a log scale, but here is the plot twist.
Ah,
Not
yes.
all signals just sit still waiting to be swept.
No, they do not. What's fascinating here is a concept called frequency hopping.
Frequency hop.
Instead of transmitting continuously on one single fixed channel, some systems switch their operating frequency from one to another.
They bounce around.
They bounce around the spectrum.
And the sources specifically mention CDMA as an example, right?
Yes, code division multiple access.
Yeah.
CDMA uses frequency hopping methods.
And they don't just hop sequentially, like 1, 2, 3, 4.
No, that would be too easy to track. This hopping is usually done in a random or pseudo-random pattern.
A pseudo-random pattern. So to a standard, static, continuous sweep, it just looks like chaos.
Complete chaos. You might catch a momentary spike on your display, but by the time your sweep completes its cycle and returns, the signal is gone.
It's already hopped to a completely different frequency.
Exactly. It makes it a dynamic challenge to track compared to a standard, static, continuous sweep.
It's hide and seek on the invisible highway.
Very high stakes hide and seek.
So who is actually doing all this sweeping? Who are the traffic cops of the airwaves?
Well, at the macro level, regulatory agencies use them heavily.
To monitor the radio spectrum.
Right. In the U.S., that's the FCC, the Federal Communications Commission.
And they're out there running these sweeps.
Continuously. They use them to ensure that users are only transmitting according to their legally assigned licenses.
Making sure a local FM station doesn't start bleeding into emergency dispatch channels.
Exactly. Keeping everyone in their legally assigned lanes.
Okay, but here's where it gets really interesting. It's not just about policing the big broadcast towers. It's about testing new electronic devices.
Oh, absolutely. Ensuring the tech actually works before you even buy it.
So what exactly are they measuring when they test a device?
Well, in a laboratory setting, they sweep RF oscillators to check for imperfections.
Because physical hardware is never mathematically perfect.
Never. So they sweep it to look for phase noise.
Which is like a smearing of the signal, right?
Phase noise. And they look for harmonics.
Unintended signals at mathematical multiple?
Right. And spurious signals. Basically, any rogue emissions that shouldn't be there.
And this isn't just for radios. The sources mention computers meant for consumer sale undergo these sweeps too.
Yes. Standard desktop computers.
Ugh.
Laptops. Because a computer motherboard is full of high-frequency components.
They're essentially accidental radio transmitters.
Exactly. So they undergo sweeps to ensure they won't cause radio frequency interference with other radio systems.
So when I turn on my laptop, it doesn't accidentally jam my neighbor's Wi-Fi.
Or disrupt a local cell tower. That's why those compliance sweeps are mandatory.
I love that. But I also really want to talk about the espionage angle.
Ah, the spy stuff.
Yes, because sweeping is how you hunt for covert listening devices. Bugs.
It is entirely validated. Technical surveillance countermeasures, or TSCM, rely heavily on these sweeps.
Because a bug has to transmit its data out somehow.
And to do that, it has to use the radio spectrum. So a security team will use portable sweep equipment.
They bring a spectrum analyzer into a room.
They sweep the room, map the baseline, and look for any unauthorized spikes on that logarithmic display.
Hunting for the delta anomaly. The signal that shouldn't be there.
Exactly. It's a critical security application.
Okay, so we've covered FCC regulations, laboratory testing, and hunting for spies. But what happens when you have to do all of this in real time under massive pressure?
If we connect this to the bigger picture, the world of professional audio provides the ultimate live test.
When you have dozens of wireless microphones.
Wireless intercoms, in-ear monitors,
Yeah.
all operating simultaneously in a confined space.
The local radio spectrum has to be perfectly managed.
It's an incredible problem. And the source material highlights American Super Bowl games as the prime example.
The Super Bowl.
Yes. At the Super Bowl, audio engineers have to sweep the radio spectrum in real time.
Because the RF footprint there is just absurd.
It's the most congested temporary RF environment in the world. So they don't just assign frequencies and hope for the best. They sweep continuously.
But they change their method, right? They don't sweep the entire spectrum.
No, that would be too slow. They limit the sweep's bandwidth solely to the operating bandwidth of their devices.
So they narrow the view to just their specific gear.
Right. Narrowing the span allows them to sweep incredibly fast while keeping the detail high.
To ensure every single local wireless microphone is operating on previously agreed upon coordinated frequencies.
Exactly. They map it all out to avoid intermodulation.
And to catch rogue signals.
Oh, rogue signals are the nightmare scenario. If an uncoordinated camera crew powers up a transmitter
The continuous sweep catches it instantly.
before it causes a dropout on the global broadcast.
Just imagine that for a second. Imagine you are watching the Super Bowl halftime show, and this sweeping isn't happening.
It would be catastrophic.
The signals would inevitably cross, the interference would generate a wall of static, the entire broadcast would just collapse.
It absolutely would. The sheer volume of wireless devices demands that level of high-stakes coordination.
So what does this all mean? We started by painting a picture of this invisible world buzzing around us.
The ocean of radio waves.
Right. And now we see how vital RF sweeping is to navigating that ocean.
It's the diagnostic tool that makes modern interoperability possible.
From the FCC enforcing regulations to keeping consumer computer electronics safe.
To hunting for covert spy bugs.
And keeping the Super Bowl on the air.
It touches everything.
It really does. So the next time you use a wireless device or you sit down to watch a live broadcast, take a second to appreciate the heavily monitored spectrum making it all possible.
Because it takes a massive amount of engineering to keep it running cleanly.
But looking forward, the sources leave us with a really interesting question.
A very provocative thought, actually.
Because consumer devices are multiplying rapidly. Everything is wireless now.
And complex technologies like that pseudo-random frequency hopping we talked about, they are becoming the standard for everything.
Not just military comms. Everything.
Right. So the question is, will our traditional methods of sweeping and monitoring the spectrum eventually be overwhelmed?
Overwhelmed by just the sheer density of it all.
The density and the unpredictability of the airwaves. If everything is hopping pseudo-randomly all the time, how do you map that in real time?
It effectively becomes a wall of continuous, unmappable noise.
Exactly. Our diagnostic tools are going to have to fundamentally evolve just to keep up.
That is a wild thought to leave off on. Something to mull over next time your Wi-Fi randomly drops out.
It's a crowded highway out there.
It really is. Thank you for joining us on this deep dive. We love exploring the invisible architecture of our world, and we're so glad you took the time to explore it with us. We will catch you next time.
Goodbye, and keep analyzing the world around you.